Okay, so everyone, welcome to week number 8. This is now lesson number 15, and we're starting with a question from the homework, which is the following: an SRS of 450 high school seniors, that's my N, gain an average of an X bar. It's normal. Sigma is equal to this. We want to estimate mu. So we want a 99.7% confidence interval AB. So we know it's going to be of the form X bar plus or minus Z star sigma over the square root of N. So X bar they gave me, it's 23.13. Sigma they gave me, it's 48.81. And they gave me, it's 450. They didn't straight up give me Z star, but they did tell me that I'm working with a 99.7% confidence interval, which means my cutoff points are going to contain 99.7% of my data. Now I know just from the 68, 95, 99.7 rule that a Z star of 3 is the right edge of 99.7%. Because my rule tells me that 99.7% of my data falls within 3 deviations. Now, if you're not happy with 3, then you could always go to your calculator or crunch it and get the more exact value of, so we'll do normal CDF. Oh, yeah, let's do crunch it instead, since that's what we do for this class. So let me stop this for a second. Now let's go to crunch it. Where, how do I get crunch it? Is there a way to get crunch it in the middle of a problem? No. Okay, so never mind. Let's use the calculator. Well, I mean, the answer is 3, but I'll just get a value in the calculator of inverse norm 0.97 in the center. My calculator gives me I'm sorry. I put the wrong number in my calculator. No wonder it was giving me the wrong answer. So again, it's not 0.97, it's 0.997, 99.7%. My calculator actually gives me a Z star value of 2.9677 ... So it's about 3. And if I plug everything into the formula, if I do X bar minus that number, I should get this. And if I do X bar plus that number, I should get this. That's the left edge and the right edge of my interval. Does that make sense?
So A is left, B is right.
So yeah, that's what they gave me here, right? A, B. A is the left, B is the right. Sure, someone else had a question or comment on this? No. Then it says, based on your confidence interval in part A, how certain are you that the mean change in score mu in the population of all high school seniors is greater than 0? So notice that 0 does not fall between these two numbers, right? My interval was 16 point whatever to 30 whatever, right? That was my answer. That's my AB. 0 is way out here. So I'm 99.7% confident that the true mean is not 0. So let's see what my options are. The entire interval is larger than 0, so we are 99.7% certain that the mean change in score is greater than 0. Seems good to me. The interval does not contain 0, so we're 99.7% certain that the mean change in score in the population of all high school seniors is greater than 0. So this does not contain 0. Does not contain 0 is not enough, because if I would have landed on the other side, it also would not have contained 0. The fact is that the interval is way bigger than 0, so it's larger than 0. That's the key. Not that it doesn't contain 0, but it's larger than 0. The upper endpoint is larger than 0, so we're 99.7% certain the mean change in score is greater than 0. It's not the upper endpoint. What if the lower endpoint was negative? Then the interval would contain 0. That doesn't make any sense. And then we cannot be certain at all If we want to make conclusions about the population mean, we should do a hypothesis test instead of a confidence interval. Hypothesis tests and confidence intervals overlap. They give you the same answer. They're just two different methods of getting the answer. So that will be the answer to that one. Anyways, are there any questions on that? Does that make sense? The approach and how we solve that one?
Yes.
Okay. Yeah.
If you don't mind, I'm actually stuck on number 6. Could you go over that one?
Stuck on number 6. Well, let's share my screen again. And let's look at number 6. This one, number 6, or you mean the 6th question, this one down here?
The 6th question.
All right. So let's take a look at what it says. It says, the National Assessment of Educational Progress, NAEP, includes a mathematical test for 8th grade students. Scores in the test range from 0 to 500. Suppose you give the NAEP test to an SRS of 900, that's my N, from a large population in which the scores have a mean 281, this is my mu, and a standard deviation 134, this is my sigma. The mean X bar is, of course, going to vary if you take different samples, right? Different samples are going to give you a different sample mean. Makes a lot of sense. The sampling distribution of X bar is approximately normal. It has mean 281. Its mean has to match. The means match. What is the standard deviation? Well, it's a sampling distribution, so it's the original one divided by the square root of the sample size. That's it.
So it's the original standard deviation divided by the sample size?
Divided by the square root of the sample size.
Of the sample size. Okay, thank you.
That is the standard deviation of the sampling distribution. Any other questions? Okay, well then let's move on. We were talking about, I don't know, what did we do? We did hypothesis testing, right? We got that far? Let's see what people are saying. I think we started hypothesis testing, right? Anyone? Dealer?
I don't believe so.
Did we finish confidence intervals at least?
Yes.
All right. Maybe we stopped right in the beginning of hypothesis testing. Although
I think you had said we were going to start a new topic, and that's why we stopped class like 5 minutes early.
Oh, okay.
Yeah.
That sounds reasonable. Okay. So this topic is called hypothesis testing. And it is one of the main, I'm not even sharing my screen, so hold on. Hypothesis testing is one of the main subsections in statistics, and certainly in this course. Confidence intervals and hypothesis testing together is going to be the next few weeks. And the idea of a hypothesis test is as follows. Suppose that you are hired by the Coca-Cola company, and you are hired to determine whether or not 2-liter bottles of Coca-Cola truly have 2 liters in them. How would you determine whether or not 2-liter bottles truly have 2 liters in them? Because obviously there's not a person who pours 2 liters into a bottle, closes it, next bottle, and so on. It's computerized, and computers can malfunction or need to be recalibrated from time to time. So how do you determine whether or not your machines are actually putting in 2 liters into a bottle? Well, how would you determine that? Oh, someone gave an answer via text. Let's see what it says. Sample, right? Wonderful. Sample, right? I love that. Oh, someone said we went over null hypothesis and the alternative hypothesis. We also went over P as a gauge on whether to reject the null hypothesis or not. Oh, you guys are lying to me then. Maybe not intentionally, but we did all this stuff already. So I don't have to give my whole spiel again. We can go right to some problems. Thank you. So can you go over it again? That's a lot. It's a whole lecture. It's a whole lecture. I can't go over a whole lecture again. If we hadn't done it, of course, I would do it. But to teach the whole thing again, I can't do. But we will review it as part of doing problems. Okay, so we will do a bunch of problems, and that will be our review, seeing it in action. Okay, so let's look at some exercises. All right, let's do number 38. Pulling wood apart. So how heavy a load in pounds is needed to pull apart pieces of Douglas fir that's 4 inches long and 1.5 inches square? Here are data from students during a laboratory exercise. Here is the number of pounds the load in pounds needed to pull them apart. We are willing to, so these are the numbers. Okay, we're willing to regard the wood pieces prepared for the lab session as an SRS of all sample pieces of Douglas fir. Just assume it's the case. Why not? What's so special about this one? Engineers also commonly assume the characteristics of materials vary normally, so we'll just assume it's normal, the other condition. So suppose that the strength of pieces of wood like these follows a normal distribution with a standard deviation of 3,000. So we're going to assume that we're dealing, make it a little, we will assume that we're dealing with a normal distribution with a standard deviation of 3,000 pounds. So blank 3,000, because we don't yet have the mean. So for now, it's just blank 3,000. Is there statistically significant evidence at the alpha equals 0.10 level against the hypothesis that the mean is 32,500? So we are testing this. Okay, is there enough evidence against this claim? This is essentially my null hypothesis. It's what I'm testing against. So if I were to write it out formally, I would write it out formally that the null hypothesis is claiming that the true population mean is actually equal to 32,500 versus the alternative hypothesis that the true population mean is what? What is the alternative in this case? What is the alternative hypothesis in this case? Read the question. I didn't finish reading the question. Finish reading the question, and then tell me what the alternative hypothesis is in this example.
31,500.
No. Don't look at B. We're on A. The question is there statistically significant evidence against the hypothesis that the mean is 32,500 for the two-sided alternative? What is the two-sided alternative to mu equals 32,500? If mu was not 32,500, give me three things that it can possibly be. Not numbers, but give me three options for what it might be. if it wasn't equal to 32,500? What are some other options? There's
So
only, sorry,
greater-
more than or greater than, less than, or what?
Equal to?
No, equal to is not an alternative. Equal to is what we have there. We need three alternatives to this. Right? We need three other possibilities. If it's not equal, it could be more than,
Different from?
different from. Okay, different from, which includes both more than or less than. Now, in this particular example, we're dealing with what's called a two-sided alternative. So what do you think in this case two-sided alternative is referring to? Which of those three options? More than, less than, or different from?
Different from.
Different from. Two-sided, either the left or the right. How do I write different from 32,500?
Plus or minus?
No. Different than. What does different than mean? If something is different than 32,500, then mathematically, what would I put in here?
It doesn't equal?
It does not equal. So the other option is that it's not equal to 32,500. So we're testing the null hypothesis. The null hypothesis is that it's equal to 32,500. And the question is there enough statistical evidence to suggest that it's not 32,500? This is our hypothesis test. And when it gives me the alpha equals 0.100 level, what this means is as follows. We're always going to compare the p-value to alpha. If the p-value is less than alpha, then what do I conclude? What do I do when the p-value is smaller? Oh, what do I do when the p-value is smaller than alpha? What is my conclusion? Small p-values tell you what?
That
The stronger the evidence against.
Good. Small p-values mean we reject the null hypothesis. Excellent. Someone wrote that in the chat. I don't see the name, but yes. Small p-values are strong evidence against. So when they give you alpha, they're giving you the cutoff. They're telling you that if my p-value is smaller than that value, that's when I will reject the null hypothesis. And if the p-value is not smaller than that, then I do not reject the null hypothesis. So what we're going to do is we're going to load up Crunch It. And Crunch It was very nice. They put all of the numbers already in here. So we go to statistics, we go to Z, we go to one sample, we click hypothesis test, it's already there. What is the mean under the null hypothesis? If the null hypothesis is true, what's the mean?
32,500.
32,500. Is it a one-sided or two-sided alternative?
2.
Two.
Two-sided. What's the standard deviation?
$3,000.
3,000. They gave me that. So 3,000. Is my data summarized or is my data? Yeah, did they give me the sample mean or do I have to calculate the sample mean myself? Do I have the summary of the data or do I have the actual data?
you have the actual data.
Yeah, I have all my data points, right? So I don't have the sample mean, which means I got to do it myself. But luckily, Crunchit can do it. All I got to do is tell it which column to work with. And I'm going to use the pounds column. So I have the sample pounds. I have my standard deviation. It's hypothesis test. This is my mean, assuming the null hypothesis is true. It's two-sided. And I calculate. So it gives me a p-value of what?
0.01.
0.01. Is 0.01 less than my alpha?
Yeah.
Yes, because my 0.01 is less than alpha, what do I conclude?
You could reject the null hypothesis.
You can reject the null hypothesis. The evidence is statistically significant. Statistically significant evidence means the evidence allows you to reject the null hypothesis. Statistically insignificant evidence tells you that the evidence is not enough to reject the null hypothesis. So that word significant is synonymous with rejection. Statistically significant, reject the null hypothesis. Not statistically significant, do not reject the null hypothesis. Part B says essentially the same question, but now what's the only difference between part A and part B? What's the
mean.
only difference?
The mean's different.
The mean is different. The mean under the assumption that the null the mean under the assumption that the null hypothesis is true is now 31,500. So when I go back to crunch it, I have to do a new one. So I go back to here, I go to Z, I go one sample. The only change is this becomes 31,500, but everything else is exactly the same. And I calculate it. And what is my mean now? Not my mean, I'm sorry. What is my p-value now?
0.3.
0.3 or 0.33, 0.32, whatever it is. So what is my conclusion at this p-value?
You can accept the null hypothesis.
Your terminology is a little off.
Or H naught. You
So-
accept H naught.
So again, we never accept anything. It's whether we reject or do not reject. So we do not reject the null hypothesis, but you don't accept it. It's like saying guilty versus innocent. Have you ever heard a court say, we find the defendant innocent? Is that what they say? What do they say in all these court shows?
Not
Not
guilty.
Not guilty.
Guilty or not guilty, right? It's all about, we can't find the defendant innocent. We never do. We just don't have enough evidence to say that the person is guilty. Same thing here. We never accept the null hypothesis, ever. It's all about, is there enough evidence to reject it? Or is there not enough evidence to reject it? Does that make sense? I guess the only time we can accept it is if we actually sample the entire population. Then we don't really have a sample, we have everything, but that never happens in practice.
Can I ask a question, please?
Yeah, of course, go ahead.
Since it was 0.3, said you do not reject it?
Yeah, because this is bigger than alpha. And when the p-value is larger than alpha, the data is not statistically significant, and therefore we do not reject the null hypothesis.
Okay, thank you.
Okay, we haven't learned what the Z-statistic does yet. We haven't looked at that yet. We're just doing one thing at a time. So let's do another one. Let's look at 39. Bone loss by nursing mothers. As discussed in exercise 16.26, breastfeeding mothers secrete calcium into their milk. Some of the calcium may come from their bones. Some mothers may lose bone mineral. Researchers measured the percent change in mineral content of the spines of 47 mothers during 3 months of breastfeeding. Here are the data. The researchers are willing to consider these 47, okay, well, that's N, 47 women as an SRS from the population of all nursing mothers. Suppose that it's a normal distribution whose sigma is 2.5%. Do these data give good evidence that on the average, nursing mothers lose bone mineral? So what would be the null hypothesis? What are we testing against here? And then what would be the alternative hypothesis? The null hypothesis is the thing that we're taking evidence in the hope of rejecting or not rejecting. So what are we looking to reject / not reject?
if it's less than 0?
Yes, well, remember, we gotta, that is the question if it's less than 0, but the question is, what do I write here and what do I write here specifically?
Do you want numbers or just statement?
Statements
So,
that will have numbers in them.
in this case, it would be to not, you want evidence to not reject nursing mothers losing bone mineral.
Okay, but now state that as a mathematical sentence. So the null hypothesis is that the average loss is 0 versus the alternative that the average loss is
not equal to 0.
well, that would be two-sided, right? That would indicate that we can also gain mineral, but we're not looking at whether they gain mineral contents, right? The alternative in this case is that they lose mineral content, right? So we're testing that the overall change is negative. This would be a one-sided test. Does that seem reasonable?
Yeah.
Okay. So what we're going to do then is we're going to go to crunch it. I could get rid of the old crunch it and put in a new crunch it. Uh-oh. Come on, crunch it. How do I? Hold on, let me stop sharing for a second. Maybe there's an issue. Nope, no issue on that end. Well, that's horrible. Come on, crunch it, don't let me down. What do I do if I don't have crunch it? How can life go on without crunch it? What if I refresh? Where are you, crunch it? Where the hell are you? Oh, here we go. There we go. Crunch it's working. Okay. So here's our data. Here's the 47 women, mothers. So we go to statistics. We go to Z. So one sample. We want a hypothesis test. What's the mean under the null hypothesis in this case?
0.
0. Is it a two-sided or a less than or greater than situation?
Less than.
Less than.
What is the standard deviation?
2.5.
2.5. They gave me that. 2.5. Am I summarizing my data where I tell you the number and the mean, or am I using the actual data itself and asking Crunch to do it for me?
Actual data.
So which column am I using? I'm obviously using the change column. So I go to the change column and I say calculate. And what does it give me? What is my P?
Less than 0.
My P-value is what? I just,
Less.
huh?
I don't know if you want me to answer it if you want to.
Go ahead. What's my P-value?
Less than 0.0001.
Less than 0.0001. Now, in the last example, alpha was 0.10. In this example, they don't really give me an alpha. So how do I know whether to reject or not reject the null hypothesis? So the answer is, when the p-value is less than alpha, we reject, right? So what are some typical alphas? 90%, or sorry, 10%, 0.10, 0.05, 0.01. Being less than 0.0001 means that there's less than a 0.0001 chance that this outcome could have occurred by chance alone. Would you take those odds when there's a less than a 0.0001 chance that something can occur?
No.
That's less than 1/100%. Something that unlikely is not going to occur by chance. Well, if it's not going to occur by chance, then what's the only reason why it might occur? The answer? No, you definitely are going to reject here, Andrew. You're definitely going to reject. Unless that was referring to something else a long time ago, I don't know. This p-value is so small that you certainly reject the null hypothesis, because remember, you reject when alpha is less than, oh, and the p-value is less than alpha, right? Small p-values you reject. This is so small, I essentially don't even have to give you alpha, because it's so small that I will reject no matter what. The likelihood of it occurring, if the mean really was 0, is so small that the only reasonable conclusion that I can make is what about the mean? Again, the
Not
like,
zero.
say again,
That it's not 0,
more specifically,
less than 0.
that it's less than 0. Okay, remember the p-value is predicated under the assumption that the null hypothesis is true. So under the assumption that the null hypothesis is true, we got a result so unlikely as to just not be possible. And therefore we will reject the null hypothesis. Make sense? So let's now talk about the other approach to hypothesis testing, which is the Z-Statistic approach. So, let's see if it's in here. So what are you confused about? Go ahead and ask. If you want. I can't force you to. It has a chance of less than 1 in 10,000, and we are rejecting, because you're basically saying that the likelihood of this occurring is 1 in 10,000, and yet it occurred. If something has a 1 in 10,000 chance of happening and it happens, would you question the assumptions? Or would you say, oh, okay, yeah, I'll go with that? Waiting for you to write something or say something. What does it depend on? If it's 1 in 10,000 chance of occurring and it happens, I would start to really significantly question whether or not my assumptions are valid. Based on how small what is. So yeah, so a small p-value makes us question our assumptions. What is our only assumption here? Our only assumption is that the null hypothesis is true. Small p-values make us question our assumption, make us question the null hypothesis. Well, if we're questioning the null hypothesis, then we only have one other option, which is the alternative hypothesis. So essentially what occurs is, assume the null hypothesis is true. If it's true, how likely is it that I got what I got? If it's so unlikely that I have to question whether my null hypothesis is true, that's when I reject my null hypothesis. And if it's not unlikely, of a result, if my p-value is, let's say, 10%, okay, a 10% chance is 1 in 10. If something has a 1 in 10 chance of occurring and it occurred, would I question everything that I know? Or would I say, okay, I didn't see that coming, but it's certainly possible and plausible and realistic. But if something is a 1 in 10,000 chance of occurring and it occurs, then I start to question, okay, is this a valid assumption? Now, in our case, we usually don't even got to go to the 1 in 10,000. Okay, we usually go to 1 in 20. If something has less than a 1 in 20 chance of occurring and it occurs, we already usually reject the null hypothesis on a 1 in 20, let alone 1 in 10,000. Now, it's up to you. You don't have to do 1 in 20, which is a 0.05 of 5% alpha. You can do a 1% alpha, 1 in 100, or 0.1% alpha, 1 in 1,000. It depends how certain you really want to be internally that your conclusion is valid. If rejecting the null hypothesis means hiring an entire new labor force, recalibrating every machine in the shop, doing this, doing that, etc., then you don't want to do that unless you know for certain that something is wrong. In that case, 1 in 20 probably won't be enough. Maybe even 1 in 100 might not be enough in that case, right? I mean, that's a personal decision. You might say, I need a 1 in 1,000 chance to make sure it's true. It depends on the situation. Does that make sense? I hope it does. It's very important because we're going to spend weeks on this. So when it comes time to testing a population mean, you basically do a few things. One, you want to check the conditions for the test that you plan to use. We only have one test so far, and that test was what? It had to come from a normal population. It had to be an SRS. I think those are the only two conditions, right? We don't have any other conditions for the first example, right? Normal population and an SRS. Now, what we did is we found the p-value. That's the approach that we've been using the entire time. There is a different approach, which is calculating what's called the test statistic. Now, Crunchit has been computing our test statistics for us. And from the test statistic, they've been getting the p-value, which is at the end of the problem, the one number that you look at to make your conclusion. But I want to focus on the test statistic now, and I want to explain what that's referring to. So what we have is as follows. We believe that it's coming from a normal distribution. That's one of our assumptions. If the null hypothesis is true, we are claiming that the mu has some specific value, which we will label as mu naught. So mu naught is the center of our normal curve because we are working under the assumption that the null hypothesis is true. And if the null hypothesis is true, it's right in the middle of our normal curve. Your data, you get an X bar value, and your X bar value is out here somewhere. That's your X bar value. So the test statistic is the value that you get that we're going to compare to the assumed value of the mean and the assumed value of the standard deviation. Remember, this is a sample standard deviation. So the sigma in this example is the original sigma over the square root of n. So our test statistic is going to be our z-score. We take our sample mean, which is X bar. We subtract off the population mean, which under the null hypothesis is assumed to be whatever value this is. And then we divide by the standard deviation, which is sigma over the square root of n. This guy here is our test statistic. And we will have a different test statistic for every different scenario. This is just the single population scenario. So what do we do with the test statistic? Well, we can do two things. One, I can compute the probability of being past it. What is the probability of being past it called? What name do we have for that in the context of hypothesis testing? That is the p-value. The p-value is the probability of getting what you got or something even more extreme, the p-value. Of course, this p-value is only for a one-sided case. If it was a two-sided case, how would I compute the p-value? Remember again what the p-value is. It's the likelihood of getting what you got or something even more extreme. So if it's a one-sided case, the only things more extreme are the things past it. But if it's a two-sided case, what can be more extreme than X bar besides these values?
Whatever is less than that value.
Sorry, say it again.
Whatever is less than
Less than what?
your value, the X bar.
I mean, all this stuff too? No, this is closer to the center. That's not less. That's not more extreme. That's less extreme. Anything to its left, that's a lot of stuff that's very close to the center. We want to be more extreme. We want to be even further away from mu naught than what we got. So if this is what I got, then all these things are further from the center than what I got. But there's other things that are further from the center. Less than their center. I don't know what that means. Less than this. No. Over here, is this point right here more extreme than what we got? Is this further away from the center than what our actual X bar is? Or is this closer to the center? Closer. So we only want the things that are further than what we got. So where are the points that are further from the center than what we got? Here's what we got. All this is further from the center, from right here. Are there any other points that are further from the center than what we got?
So what you're saying is if you reflected the distance from the right side over to the left, and then we measured whatever's from that point and towards the left is.
That's right. All this stuff from negative X bar to the left is also further from the center than what we got. So for the one-sided test, we just compute this. For the two-sided test, we got to compute this plus this. But by symmetry, it's easy to do that. What do I do to this value to get the total amount if it's two-sided? I just multiply it by 2. The area on the left is exactly equal to the area on the right. So if it's one-sided versus two-sided, the difference is the p-value doubles for the two-sided case. Whatever you get for the one-sided case, you just double it. In fact, I'll show you that. Let me show you. Let's go back to crunch it for a second. This p-value is too small to really see it in action. So let's come up with a different scenario for Z. Let's instead get let's see what -3 gives me. Okay, much better. So -3 gives me this p-value. That was for a one-sided situation. If the only change I make now is to make it a two-sided, then what do I expect to happen to my p-value?
To double.
It should double. Did it double?
Yeah.
Yeah, right. If you do 0.05, if I do my calculator, 0.05366 times 2, my calculator gives me 0.10732. The only difference between a one-sided and a two-sided is that the p-value doubles. Notice that the Z-statistic did not change. because the Z-statistic doesn't care if it's one-sided or two-sided. The Z-statistic is a computation based upon your sample mean, the assumed mean, the sigma, and the square root of n. In fact, if we take out a calculator and we do x bar, which in our case was negative 3.587, minus the population mean, which is negative 3, divided by sigma over the square root of n, which is 2.5 over the square root of 47. So my calculator gives me a Z-statistic of negative 1.0697077, which is obviously where this comes from. Okay, it's simply the Z-statistic is nothing more than what you get by following the formula. Z-statistic. So once you have the Z-statistic, then you can compute the p-value, which is the likelihood of being past it. For one-sided, it's going to be past it. For two-sided, it's going to be past it or past its symmetric partner, which is why the p-value doubles. Everything else remains exactly the same. Notice here, population mean equals negative 3. This is one-sided, and this is two-sided. Does that make sense so far? I hope so. We'll do plenty of problems. We will do plenty of problems.
Did you repeat the? Oh, never mind. Did you erase it?
Oh, it's there.
Okay. Can you repeat the one-sided and two-sided part?
The one-sided. So my value for this example. So let me do a new picture that is more for this particular example. So we are assuming that it's normal. We're assuming that the population mean is negative 3, which is right here. My sample mean is negative 3.587. I'll just write negative 3.6 because I have no room. So that's my sample mean. Okay, that's what I got right here. If this is my data, this is my data line. If I compute everything to a z-score, then negative 3 being the mean will become 0. And negative 3.6 will become negative 1.6. Right? That's by following the formula z equals x bar minus mu over sigma over the square root of n. My p-value is the probability of being in here because it's one-sided, less than. In my case, it gave me a 5% chance. If I were to do is not equal to, then I would also consider the possibility of being on the other side of negative 3, which is negative 2.4 or positive 1.6. And I would just also compute the probability of being in here, which is now twice what it was before. So my p-value before was 0.05, 5% chance, and my new p-value is now 10%. Two-sided tests are always harder to reject because p-values are always bigger for two-sided tests, right? And we want small p-values to reject. So two-sided tests are harder to reject because your p-values are going to be bigger. Does that make sense?
Yes, thank you.
Sure. X bar equals sample perspective, Z equals statistic perspective. Yeah, that's a good way of thinking about it, right? I mean, the X bar is the actual data, the actual sample, whereas Z is in terms of the relationship to center, whatever it happens to be, without caring what it actually happens to be. Because in every Z-score, the center always becomes 0. And the deviation always becomes 1. And then you're just about how far am I from the center? Whereas my actual numbers, that's what the X bar is. So crunch it will give you both the Z-statistic and it will give you the p-value. Two different approaches, or two different things. you need the Z-statistic to get the p-value. Let's see what other testing my skills I can come up with here. So let's just do some multiple choice. Number 19. You use software to carry out a test of significance. The program tells you that the p-value is p equals 0.011. You conclude that the probability computed, assuming that H naught is blank. So read the three possibilities. And then I'll give you a minute or two to think about it. And then what I will do is I will do my usual fun multiple choice type thing. Oh. Okay. So who here by a raise of, not a raise of hands. Never mind. I kept thinking we were in class for a second. I'll go ahead and just type in A, B, or C. And pay no attention to the man behind the curtain and all previous answers. Just do what you think is correct. So I see some A's, I see some B's, I see a not sure, which is always fine. I see a C. I see some not sures. I see a B and a not sure. Hedging your bets there. That's cheating. Okay, that's not a problem. All right, let's take a look at what we have here. Absolutely no idea, someone said. So you use software to carry out a test of significance. The program tells you that the p-value is p equals 0.011. That's a pretty small p-value. That's about 1%. So remember, if the p-value is less than alpha, then we reject. And if the p-value is greater than alpha, then we do not reject, right? It's all about the p-value and the comparison to alpha. Don't reject. Okay, so we got a very small p-value. So I conclude that the probability computed, assuming that H naught is true, remember, we always work under the assumption that the null hypothesis is true. So right off the bat, I'm going to cancel C. We always work under the assumption that the null hypothesis is true. It says the probability of getting what we got or something even more extreme, assuming the null hypothesis is true, is 0.011. So the probability of a test statistic taking a value as extreme, more than extreme than the actual value is this, and not less extreme, no, more extreme. What we got or something even less likely, something further from the center, the answer is without question A. Answer. Okay, this is the whole idea of what the p-value is. It's the probability of getting what you got or something even less likely. if the null hypothesis is truly true. Hopefully that makes sense. Go ahead, number 20. Read it, think about it. I'll give you a minute.
What was the second part of the p-value? You said it was probability of what you got or less than what you got?
No. It's the probability of getting what you got or something even more extreme than what you got, which means further from the assumed mean. So if the mean is 5 and I got a 10, it's 10 or more. If I got a 0, it's 0 or less. More extreme than what I got under the assumption that the null hypothesis is true. That is what the p-value is. So you use software to carry out a test of significance. The program tells you the p-value is p equals 0.011. This result is A, not statistically significant. Well, you can read it. I don't have to say it, but anyone reading this will be able to read it. So go ahead if you think you have your answer, write it down, A, B, C, or not sure. I don't know. I don't care. Why am I taking this course? Isn't there some life choice I could have made that would not have landed me here? I say that to myself every day. You have other options. But I'm going to give you a couple seconds. I want you guys to think about it. So what do I have here? I have some not sures. I have some B's. I have some C's. I have an A, but maybe that was what the last question? I don't remember. B, 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 C. I think the A was the last question. So lots of B's. At this point, we can just be like, well, so many people were saying B, I'll say B. So let's take a look. Use software to carry out a test of significance. The program tells you the p-value is p equals 0.011. Is the p-value less than alpha? That's all that matters. Is it less than 0.05? Yes. So it is statistically significant for 0.05. Is it less than 0.05? Yes, it's statistically significant. Is it less than 0.01? No, not statistically significant. So there's your answer, is B. Oh, there's no check answer, but it is B. It's all about the comparison of the p-value to alpha. Statistically significant means less than alpha, hence reject. All right, last one for now. Number 20, well, for this section, number 27. The Z-statistic for a one-sided test is Z equals 2.29. This test is A, not statistically significant, that either alpha equals 0.05 or alpha equals 0.01, or B or C. So think about this one. You might even need to do a calculation for this one. In fact, you do, so I'll do it here. Hold on, don't put your answers in yet. I'm gonna because I have to know where the last one ended and the new one begins, so I have to put one in first. How do I? Okay, so now you can go. Now that I have a benchmark. Ooh, I got some C's, some B's, and some A's right off the bat. With a not sure. Hold on. So Hindi ko alam. Hindi ko alam. That must be, I don't know. What language is that? Filipino. I don't know any Filipino. I did Kali and Eskrima and Arnis for a few years back in the day when I was back in my martial arts stage. Those are pretty much the only 3 words in Filipino that I know. But that was fun back in the day. Knife fighting is always cool. Now I just have delusions of grandeur. So you're going to teach us some moves or what? Well, if I was in person, I could, but I'm not sure how effective they would be. I did not do karate. I did a, back in the day, years ago, before I began, martial arts was very segregated in the sense of you would learn one discipline and you would not venture and do like a hybrid. So, different types of karate, there was judo, there was all these different things. And then Bruce Lee came into the picture in the 60s. Yeah, and then Bruce Lee did a Wing Chun, which is a type of Kung Fu. His master was Yip Man, very, very famous. And then Bruce Lee came to America and he created what is called Jeet Kune Do, the way of the intercepting fist. And he created Jun Fan, which was a style that I actually studied. I actually trained with Danny Dos Santo, who was Bruce Lee's #1 student here in, he's in Pasadena. No, not Pasadena. He's in Marina Del Rey. So I did that for a few years. That was like 15 years ago. But anyway, so Bruce Lee kind of, well, I used to live a little further south than I am now. But Bruce Lee kind of took all these different arts and combined them together and said, you know what, this works, this doesn't work, take this, adapt this, change this. He actually saw a Muhammad Ali fight and said that he based his style significantly on Muhammad Ali's footwork, because Wing Chun was an art that was very strong base, not a lot of movement. You're very close. And, Muhammad Ali was moving all over the place and stick and move. And Bruce Lee said, hey, that's a lot better. So he adapted. Anyway, so what I did was a blend also. I'm from Chicago. So there was a blend in Chicago that I did, 27 different martial arts, and did a little bit of all of them. It was a lot of fun and I lost a lot of brain cells. But anyways, back to the original problem. Number 21, the Z statistics. So what are our answers here? Watch you hit yourself. I don't hit myself. What the hell? So anyways, so lots of C's, some A's, some B's, all over the place. Okay, so how do we do a problem like this? We do like the following. We assume a normal, because we always assume a normal. And Z equals 0 is right in the center. And we got a value of 2.29. 2.29. And the p-value is the probability of being past 2.29, more extreme than what we got. How do I know it's only one side, not the other? Because it said it's a one-sided test, not a two-sided test. So we just need the p-value here. So what's the probability of being past 2.29? Well, I have crunch it, so let's go to crunch it. How do I load up crunch it? Did I already have crunch it? Oh, did I knock off crunch it? How do I get crunch it back? Oh, I have no crunch it, so I'll do it on my calculator instead. My calculator says that the probability of being past 2.29 is, and you can do this on crunch it or by yourself, I got a p-value of 0.012. So a p-value of 0.012 means that if p-value is less than alpha, it is significant. Is the p-value less than 0.05? Yes, significant. So it's not A, because A says not significant. Is it less than 0.05? Yes, it's significant. Is it less than 0.01? No, so it's not, oh yeah, so that's it, right? It's significant at 0.05, but it's not significant at 0.01. So the answer is B. Fun times. That was fun, right? Let's do number 23. How do I, okay. Hopefully this is, how did you get 0.012? Oh, it's a calculator. I just did the probability of being past 2.29. You can either do it on a calculator, you can do it on Crunch It, you can do it in a table, but that's just calculating the probability of being past a specific value. Can you divide by itself? What does that mean? Can you divide by itself? What software do I click on Crunch It to enter it? So let's find, we'll come back here in a minute. Let's find a Crunch It. Sorry, you don't have access to the book? Why I don't have access to the book? I've had access to the book the whole time. What is happening here? Let's try this again. Oh, here's the book. Let me just stop sharing for a second, just so I can more easily get to a Crunch It link. Here we go, Crunch It. Okay, back to sharing. Sorry, I'm sleep deprived and letters are not making sense. I meant, how do you do it on Crunch It? Well, let's load up Crunch It. So I don't know what these are. I can just file new. Okay, so statistics. We want a probability of being past was it 2.26, 2.29? What was the number? Anyone remember?
2.29.
2.29. So I go to distribution calculator, I go to normal, and the mean is 0, deviation is 1, and I want to be greater than 2.29. Calculate, so it should give me 0.0122 or 0.011, which is fairly close. So my Z statistic was 2 point something, and I had a 0.011 chance of being past it.
And the mean is 0 and the standard deviation is 1 because it's a normal.
Because it's a standard normal.
Okay.
Standard normal always gets 0, 1. All right, so how do I get the book back? Okay. Experiments on learning in animals sometimes measure how long it takes mice to find their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause the mice to complete the maze faster. She measures how long each of 10 mice takes with a noise as stimulus. The sample mean now is 16.5 seconds. What is a null hypothesis for this significance test? Take a minute or two and think about that. Ooh. So let's get some answers in here, guys. Come on. All right, so let's see what we have. Some not sure's. I got some A's, I got some B's, some C's. Okay, first of all, the null hypothesis comes before you do a sample. 16.5 is your sample results. It has no bearing whatsoever on the null hypothesis or the alternative hypothesis. That's first of all. 16.5 is your sample outcome. The sample outcome comes later. It's when you do your sample. Second, you are testing against the equality. The null hypothesis always gets the equality. There's no exceptions to that whatsoever. The null hypothesis is what you're testing against. The fact that I got 16.5 certainly means that I might conclude that mu is less than 18, but that's what I'm testing against. Okay, I'm wondering, maybe this is wrong and it's the alternative that's correct. So what did someone say here? Would it be C because you were trying to see number? No, the null hypothesis is not what you're hoping or checking if things are different. It's what will be the case if it wasn't different. You are trying to determine whether or not the mean has changed or has dropped or has gone up from the assumed value of 18. So the answer to A, so the answer to 23 is A. Now, what is the alternative hypothesis for the same problem? So write out what you think the answer is.
Professor,
Yes.
why was it B for 17.23 or question 23? Because
It wasn't. I had scrolled down.
Oh, okay.
Sorry about
Because
that.
it was
Yeah.
before I took the sample. Okay.
Yeah, exactly. I had scrolled down. Sorry about that. So the question is, what's the answer to this one? So let's see what people say. Wait, why was it B for the first one? It wasn't B, it was A. I changed it. So I scrolled down. Okay. Okay, so let's see what this one is. First of all, the null and the alternative hypotheses have nothing whatsoever to do with your sample. C is immediately out. That is your sample result, which has got nothing whatsoever to do with the null and alternative hypotheses. The null hypothesis always gets the equal sign. So 18. It's either not equal to or less than. These are both valid alternative hypotheses. But what exactly is she theorizing? She is theorizing that the loud noise is going to make the mice complete the maze faster, which means she's theorizing that the time will be less than 18. Not equal to means she's perfectly happy with more or less. No, she's not perfectly happy with more or less. She is testing to see whether or not it is less. So the answer is A and then B for 24.
I have a question.
Yes.
So the alternative is basically what you're testing for.
It's the alternative is what you're checking. Is it really this? I guess will be a good way of thinking it. Is it really this versus what you thought it was going in? Is it really less than 18? Because until now it's been 18. So the null hypothesis is that why would things change? It's 18 before, it's 18 now. But no, I think it might be less than 18. Let me check. Right? So,
Okay.
so the alternative is what you're checking. And then the question is there evidence in support of the alternative, or is the evidence in support of the null hypothesis? Can I reject the null hypothesis, or can I not reject the null hypothesis? What does the evidence tell me to do? Does Google Maps use this in computing driving times? I don't know what the algorithms are. That's above my pay grade. I'm sure what they do involves statistics, because it's staggering that they can give me a drive from the Valley to Long Beach, and I get there within a minute or two of what they project. Right? Have you ever experienced that? A significantly long drive, and the time is. I mean, I use Waze personally. And it's amazing sometimes that it'll be within a few minutes of what they project. So how do they project that? They see your routes, how many miles, your average speed at different times of day on those routes, and the various statistically significant traffic patterns, and et cetera, et cetera, et cetera. I'm sure they take all of that into account in some kind of algorithmic processes. People a lot smarter than me were able to figure out. That's above my ability. I just teach this stuff and I let other people actually use it. I'm the guy in the zombie apocalypse who can't actually do anything. I can't fix the refrigerator or get the power running or anything because that's really practical. I'm just the guy that you want because you always want one fat guy who's too slow, so the zombies eat him and everyone else escapes. That's me. So that's my contribution to the zombie apocalypse. Although I am surprisingly fast, as my tennis opponents quite often passive aggressively compliment me upon. Oh, you're surprisingly fast. Thank you so much for telling me that I'm fat. It's really, really sweet. But yes, oh my God, you play tennis. Yes, I am on 2 tennis teams. I am a 4.0, which is not the greatest, but it's it's I can hold my own against most people, I guess. Yeah, and you are the guy that lies about knowing a cure. I got the mullet for it. Oh, that was awesome. Okay, Serena Williams, though, she can probably beat me. No, she can definitely beat me. I'd wait like 20 years to play her. By that time I could probably beat her. Although I'd be like 60 something, so I don't know. Automatic game for me. It was a good line. Anyways, are there any questions? We are going to finish here. We've done 16 and 17, which is the basics for confidence intervals and the basics for hypothesis testing. And yeah, if I could grow a mohawk, I probably would. But anyways, 18, 19, 20, and the road chapters that are coming expand upon the confidence intervals and hypothesis testing. And basically what we do is we just come up with a bunch of different formulas I can beat her in chess, I know that. But anyways, we would come up with different formulas for this case and for this case and for this case and for this case and for this case. And then it's merely a matter of, okay, what am I given? Which case am I referring to? Which formula do I use? And then plugging it in. Luckily, Crunchit does all that for us. If I go back to Crunchit for a second, you'll notice that when I go to statistics, I have Z, 1 sample, 2 samples, T, 1 sample, 2 sample prepared, and proportion 1 sample, 2 samples. So there's 2, 5, there's 7 different scenarios, and any one of them will have a hypothesis test and a confidence interval possibility. Whether it's T, paired, hypothesis test, confidence interval. Z, 2 sample, hypothesis test, no confidence interval. Even better, we don't have to worry about that one. So all these different scenarios that we might come up with are just different situations. And no, it doesn't get harder. It's just apply it to this case. Now apply it to this case. Now apply it to this case. Now apply it to this case. And we're going to learn all the different cases. And Crunchit will do the work for us. Okay, but the basics are the understanding of what a p-value is, what a test statistic is, what statistically significant means, and whether or not we want to reject or not reject the null hypothesis. And once you have all that, you're done. Have you finished those chips? I did finish all those chips. They're all gone. And I don't know about the final. I don't, yeah, I know. I ate them all in one day. I said I'm fat. What do you want? Although I woke up this morning and my fingers were itching. And so I went online to do like a symptoms, and it said that it's a symptom of diabetes. And then I remembered that like 2 years ago, I got prescribed with pre-diabetes and I didn't do anything about it. So now I'm thinking maybe I should stop eating so much. We'll see. I don't know. I'm stubborn and I'm stupid. So I actually told my dad today, he was going out, and he said, should I get root beer? And I go, you know what? How about we stop with the root beer for at least a day? We'll see what happens. The chips were called J's. No, not Dr. Pepper. Not Dr. Pepper. Ugh, disgusting. I know I gotta take care of myself, but I'm lazy. I know you're not telling me anything I don't know. But anyways, so the chips were called J's. Hot stuff, good stuff. Itching hands means you're going to get some big money. Well, in that case, give me more. Oh, disgusting, Ryan. Just disgusting. Well, the diet was supposed to start on the day after my birthday, which is now in 11 days. So I was thinking of starting the diet on the day after my birthday, which is the 25th of October, which is a Sunday. But now I'm thinking maybe starting it a little sooner so that I don't, die or anything like in the next week or two before my diet. But I will tell you this though. I know what I'm gonna eat on my birthday. I'm gonna type it in because it's a hard thing to type, or at least to say. But if you guys have not been here yet, I think this is it. This is a restaurant in Koreatown called Sannangdan. And if you have never been there, it is unquestionably the tastiest food that I've ever had in my life. So if you have a chance, it's a Korean barbecue place, but it's not like an all-you-can-eat Korean barbecue. It's not what they do. You know what? I'm gonna share something with you. Nobody do anything. Hold on. I'm gonna share you their signature dish as an image here because it is just amazing. And I want all of you to bask in this. Hold on, I'm gonna get a good picture. There we go. That's a good picture. Okay, so I'm gonna share with you right now this dish, which is just amazing. I should be sponsored. And here we go, baby. This dish that they have is just the most amazing thing that I've ever had in my entire life. It is just awesome. It's also like $100 for a bowl, so it's kind of expensive. Usually you go there with like 2 or 3 people and you have this nice sized bowl, and it's just, I know I'm recording because this is important. Everyone in the world should know about this. Okay, this is like the greatest food ever. So I'm gonna have that for my